Okay, in this chapter, we will learn how to solve second-order linear differential equations. Anything can be written in this form. Equation 1. We call this second-order linear homogeneous equation. Okay, now look at the right-hand side, g sub t. That's the only term without y term. Okay. So if g sub t equal to 0, then we got equation 2. We call equation 2 second-order linear differential equation homogeneous. Okay, so we call equation 2 homogeneous second-order linear equations. Okay. So in general, we still don't know how to solve equation 1 and 2. In this section, we concentrate on solve second-order linear homogeneous equations with constant coefficient. In other words, p sub t, q sub t, r sub t, they are very simple functions. They are constant. So we will learn how to solve this, like equation 3. Before we solve it, let's look at the example. Y double prime minus y equal to 0. Okay. Obviously, in this example 1, this equation is linear homogeneous with a constant coefficient. With a here is 1, b is 0, and c equal to minus 1, right? Okay, so before we do anything, let's look at what are the solutions of second-order linear equation looks like. Okay. Now, for example, let's try this. Y equal to e to the t. Now, let's say this one is a solution. Okay. What do we mean is a solution? That means you take this one back to the equation, let's say give a name, equation 4. Then the left-hand side would equal to right-hand side. Okay. Now let's put it back in the equation. In order to do that, we need to take a derivative, right? Because there's a y double prime there. Okay. So y equal to e to the t. Take a derivative. E to the t, you take a derivative, give itself. Okay. Double prime is still e to the t. So we put this one back to the equation 4. So y double prime minus y double prime is e to the t, minus y is e to the t. Give you 0. Okay. So the left-hand side equal to right-hand side. Therefore, we got one solution. Okay. Now I claim e to the negative t is also a solution. You can check that. Okay. Let's check that. Y prime equal to, take a derivative, give you negative e to the negative t. Take a derivative again, give you negative e to the negative t. So give you positive that. Again, y double prime minus y is equal to e to the t minus e to the t, give you 0. So that's another solution. Okay. You can check this. This is also a solution. Okay. In general, anything right in this form will be a solution of equation 4 with C1, C2 arbitrary constants. Okay. So this example gives you some ideas. What do we expect for the solutions of second-order linear equations? We have 1 e to the t, and e to the negative t is another one. Then you add them together, give you another one. Anything right in this form will be solution. Okay. Don't take this for granted. Linear combination of two solutions are still solutions. This is only true for linear homogeneous equations. Okay, now next. Then you will say, how do you know y equal to e to the t is a solution? Okay, that's what we want to find out in this section. Okay. Now let's go back to our general solution. Y double prime plus by prime plus cy equal to 0. Okay. So now let's try this kind of solution. Y equal to e to the r times t. Okay. We don't know r there. We want to choose r such that this one is the solution for this equation. We call this equation 3. Okay. So let's see what kind of equation r should satisfy such that this one is a solution. Okay. So what do we need to do? Just put it back in the equation, right? Make the left-hand side equal to right-hand side. Let's take a derivative first. So take a derivative of y, give you r e to the rt. Okay. Take a derivative again, give you r squared e to the r's of t. Okay, when we put it back in the equation, you got a, replace y double prime by r squared e to the rt. Replace y prime by r e to the rt plus c times y is e to the rt. So if this one is a solution, then the left-hand side should equal to right-hand side, right? Okay. And this one, every term have e to the r, rt. E to the rt equal to 0. And we know e to the rt, this function, for any t, that will never be 0. Therefore, that means this one must be 0. We call this characteristic equation. Okay, what that means? That means if r is a solution of this quadratic equation, let's call this 5. If r is a solution for this quadratic equation, then e to the rt, where is it? Then this one will be the solution of equation 3, right? Okay. So by doing this, we change solving a differential equation to solve a quadratic algebraic equation. Okay. So this is a quadratic equation. Then the solution of like 3 situations. Quadratic equation. The first case, you got 2 real distinct zeros. Say R1 is real, R2 is another real zeros for equation 5. They're not equal. Okay. The second case, you got 1 repeated zeros. Three, we'll say R. 3, you got 2 complex zeros. R1, R2. Okay. In this video, we only consider the first case. Okay, let me summarize so far what we have. We want to solve equation 3, which is a second-order linear homogeneous equation with constant coefficient. And that means A, B, C here, they are constant. Okay. To solve this equation, we try this kind of solution. Okay. We want to find R such that this one is a solution. So we put back in the equation. Then we figure out if R is a solution of equation 5, which is a characteristic equation for equation 3, then e to the rt will be the solution. Okay. Okay. Now, let's consider the first case. Okay. Let me put it here. We have like a double prime plus by prime plus cy equal to 0. Its characteristic is ar squared plus br plus c equal to 0. Now, let's say we have two zeros. One is R1, one is R2, and they are not equal. Okay. So in this case, we will get two solutions. One is e to the R1t. Second, another solution is e to the R2t. And then anything can be linear combination of those, R1t plus R2t will be also the solution. And in fact, we call this a general solution. In fact, any solution for this equation 3 can be written in this form, will be written in this form. So what that means, if you want to solve equation 3, what you need to do, write down its characteristic equation, which is a quadratic equation. Then find its two zeros. If those two zeros are real distinct, then e to the R1t is one solution, and the e to the R2t is another solution. And all the solutions can be written in this form. We call general solutions. Now let's look at the example. Let's go back to example 1. Okay. Let's solve this one. Y double prime minus y equal to 0. And y0 equal to 2. And y prime 0 equal to negative 1. Okay, so this is a second order linear homogeneous equation with constant coefficient. As I said before, in this case your A is 1, B is 0, C is negative 1. Therefore, its characteristic equation is R squared minus 1 equal to 0. So this quadratic equation is easy to solve. Just you can factor that R minus 1 and R plus 1 equal to 0, right? So you got two zeros. They're real and different. Okay. So the general solution can be right. Okay, so you can tell. Okay, y1 equal to R1t. R1 here is 1, right? So e to the t is one solution. Y2 equal to R2t, which is e to the negative t. Okay. So the general solution is like this. C1 e to the t plus C2 e to the negative t. You can try that. Put this one back to this equation. You're going to see for arbitrary C1 and C2, this one will be a solution. Okay. So for the second order differential equation, you're going to have two constants. Therefore, we need two initial conditions to determine those two constants. Okay. So for arbitrary C1 and C2, they will satisfy this equation. Okay. However, if you want to y0 equal to 2, y prime 0 equal to negative 1, then we'll have to choose C1 and C2 specifically. Okay. So now let's find, let t equal to 0 here. Let's take derivative first. Okay. So y prime t is equal to C1 e to the t, then plus C2 e to the negative t. You take a derivative, give you negative. Okay. So let's y0, okay, y0 equal to 2. On the right hand side, let t here equal to 0. So you got a C1 e to the 0 is 1 plus C2. Okay. On the other hand, we have y prime 0 equal to minus 1. Okay, from here, let t equal to 0. So you got a C1 minus C2. Okay. Now, if we add those two equations together, the left hand side 2 minus 1 give you 1. The right-hand side give you 2C1. So this means C1 must equal to 1/2. Okay. Then we can find C2 by subtract of two equations. So left-hand side give you 3. Subtract two equations. The right-hand side give you 2C2. This means C2 must equal to 3/2. So finally we find y there is 1/2 e to the t plus 3/2 e to the negative t. So what is this? This one is a solution for this equation. At the same time, 1 t equal to 0, your y will be 2. 1 t equal to 0, your y prime will be -1. Okay, now let me summarize what we learned here. In this section 2.1, we concentrate on how to solve equation 3 here, okay, which is a second-order linear homogeneous equation with constant coefficients, which means A, B, C, they're all constants. For this kind of equation, how do we solve it? First of all, write down its characteristic equation like this, which is a quadratic equation. Solve this quadratic equation, you'll find two zeros here, R1, R2. Then e to the R1t will be your one solution. E to the R2t will be another solution. And all the solutions of equation 3 can be written in this form, okay, which is a linear combination of the y1 and the y2. There will still be solution, and all the solutions can be written in this form. That's why we call this one general solutions. Okay. So once you got the linear equation with homogeneous with constant coefficients, find its R1 and R2, which is zeros for quadratic. So we did this.